All right, we're going to start a topic about conditional probability, and it's a tricky topic. I will say it takes some time to get the hang of. I do have full confidence that you'll get it, but I do also have confidence that a number of you will struggle with it at first. So my encouragement to you is stick with it, persevere, because you will get it. But it does take a little bit to get the hang of it. All right, so we'll start out with a little introductory here. Here's some information on the Titanic about how many people were on this boat. So if you're, right here is what class you're in, first class, second class, third class, or a crew member. And then how many of them lived or died from each one of those. So first class, here's who survived and who died. So here's the question I want to ask you, and I want to say, what's the probability that a third class passenger survived? Okay, see if you can pause it and answer that out. All right, well, believe it or not, tucked in this simple question is actually a little nuance that's tricky with probability, because there's actually two events here. And see if you can pick out what are the two events that are happening in one sentence. Well, the first thing that's happening is that I'm telling you that they're third class passengers. Okay, so that's event number one. We're going to put it right down here. What are the two events? The third class passenger, or if you wanted to put it in a better sentence, someone is a third class passenger. Third class passenger. The other event that happens here is that they survive. There's your second one. So here's what I did not ask you. I did not ask you, hey, what's the probability that you pick someone on the boat and they were a third class passenger who survived? I said, what is the probability that a third class passenger, I told you that this was given. That's what we're going to say. We're going to say that's given that someone was in third class. Okay? So which one was given? This one right here, the given one, is this one. Well, the moment that you phrase it like that, when it's given, what that does is it narrows down your population. Instead of talking about all the people that were on the boat, we are only talking about third class passengers. Okay? So if I was trying to make this probability on the bottom of it, I'm going to put 178, but I'm also going to put a 528. So we're going to add up these numbers because these are the total number of third class people. Now I want to point out with extra special attention here, there's two numbers here, because many of you are going to be asking me later, why are there two numbers in your denominator all the time? And it's because of this right here. There's two numbers that make up your third class passengers. Now, want to pick survivors. Of those two numbers, which one are we going to pick? The one on top or the one on bottom? Well, hopefully it's clear we're going to pick the 178, right? Now, that 178, how would I characterize that in the words that we've been using so far? Notice that 178 belongs in two categories. It belongs in category number one, which is third class passengers, but it also belongs in category number two, which is called survivors. Okay? So it does two things at one time. It is in category one, and notice the word and, it's in category two. We call that the intersection. The intersection is the things that belong to two categories at one time. So this top number is the number that lies in the intersection of the two events. So a few things that we got to point out here, because they're going to keep coming up. The intersection number goes on top. There's going to be addition of two numbers on the bottom, and also point out you're seeing the same number show up twice, once in the numerator, once in the denominator, and that will be a pattern that always or very often comes up over and over again. Okay, so how could we rephrase this question so it fits statistics a little bit better? So instead of saying what's the probability a third class passenger survive, we're going to call it this. We're going to say given, and that's the important word, that a passenger, given that a passenger is in third class, is in third, if I can write, class, what's the probability they survive? Okay, It's called a conditional probability. The condition is that they already belong to one group, and which narrows it down to a smaller group of people out of the whole total, and then we find the probability. Okay, the notation goes like this. We're going to call it what's the probability, and we're going to call it of B given A. Well, P, we know that that's probability. So this is the event that we're having. We're finding the probability of this. So for this one, you're going to find the probability of that event given that this one has already happened. So find the probability that someone's a survivor given that they were in third class. Okay? I'm going to model it right off this formula up here. The probability of B given A. In the numerator, you're going to put the intersection, because this number belonged to both of them, of P, A and B. And then on the bottom, you're going to put, notice what's on bottom, all the ways that you can be in third class, and that is our given event. Okay, our given event. Okay, so you're going to have the intersection on top and the given event on the bottom, and there's always going to be two ways that you can do that given event. All right, like I said, it's tough and there's some nuances here, but I expect you'll be okay with it after you try it. Okay, let's get into it. Shoplifting detectors located at the exits of a department store are intended to sound an alarm when an unpurchased item passes through. 95% of bags that contain a shoplifted item will trigger the alarm. So sometimes the alarm just doesn't work for whatever reason. 8% of the bags that do not contain a shoplifted item still trigger the alarm. So sometimes this thing's going to go off when it shouldn't. Also, we know that about 1% of all bags contain a shoplifted item. We're going to set up a tree and then answer the questions. Looks like my questions got cut off, so I'll answer them on the next page. Okay. So your head might be spinning right now and saying, I don't even know what you're talking about. I don't even know how to begin to answer this question. Well, the first thing you have to do is you have to identify the two things that are going on here. There's two things in this story that are happening, and sometimes they can be subtle. The first thing that is happening here is that someone is shoplifting, or not. So someone chooses to steal. We're going to call that our first event. We'll call it event S. We could call it A and B, but I like S because it's shoplift and it helps me remember what it is. After shoplifting, what happens is that the alarm goes off, or it does not. Okay? So those are your two events that are going to happen. Shoplifting and then the alarm going off. I also want to introduce a little symbol to you. This symbol right here, this little squiggle, that means not. So if I use event S, that's that they shoplift, and if I put squiggle S, that means not shoplift. They don't shoplift. Okay, so we're not going to come up with a new letter. We're just going to write not S for that one. All right, so we're going to set up a tree, and the tree goes like this. First of all, you start out with yourself, and you think about what event has to happen first. Does someone decide to shoplift, or does the alarm go off first? And hopefully we understand that someone has to shoplift before the alarm can not or not. So the two things that can happen is someone shoplifts, or they can not shoplift. Vast majority of folks are honest. They can not shoplift. Some do. So right here it says, suppose that 1% of bags contain a shoplifted item. So the probability that someone's a shoplifter in this case, right behind it, we're going to put the probability at 0.01. We're going to use our idea of complements. Write down if there's a 1% chance that someone is a shoplifter, the probability they're not, hopefully we all understand, is going to be 0.99. All right, after that, what can happen is that either the alarm sounds or the alarm cannot sound. The alarm does not go off. So, same thing down here. If someone doesn't shoplift, either the alarm sounds or the alarm does not sound. So there's four things that can happen, and that information is right in here. It says 95% of all bags that contain a shoplifted item will trigger the alarm. So if someone's a shoplifter, the alarm, we're going to put a 0.95 by that one because 95% of the time, if a shoplifted item goes through, it will trigger the alarm. Okay, hopefully it's clear. If there's a 95% chance that it does, what's the probability that it doesn't? Well, hopefully you said to yourself 0.05. Down here, let's continue reading. 8% of bags that do not contain, so they're not shoplifters, still trigger the alarm. So not shoplift, but still trigger the alarm is going to get a 0.08. And we'll just use our idea of complements once again, that if there's an 8% chance that it does go off, that there's a 92% chance that it does not go off. All right, now we're going to find what I call our intersections. I want to find the probability that two events happen. The two events being, well, we'll start out, the first one we'll find with, what's the probability that someone shoplifts and the alarm goes off? Shoplift and the alarm goes off. Well, if you remember your intersection, you just multiply them. So we're going to go 0.01 times 0.95, and we're going to get 0.0095. So right behind it right here, I'm going to write this out, probability that someone shoplifts and the alarm goes off. I shouldn't have written this squiggle here. It's going to get in the way. I'm going to get rid of it. The probability that both those things happen is 0.0095. All right, what's the probability that someone shoplifts and the alarm does not go off? Both of those things, 0.05 times 0.01 times 0.05 is going to be, that E-4 means slide your decimal places 4 places to the left. So we have the probability of shoplift and the alarm not going off is going to be 0.0005. All right, what's the probability that someone does not shoplift and the alarm goes off? So 0.99 times 0.08, just multiplication each time, so 0.0792. And the probability of not shoplifting and the alarm not going off is going to be equal to 0.92 times 0.99, which is going to be 0.9108. All right, so I want to call attention to a couple numbers here. First of all, if we're looking at this, the probability that someone shoplifts and the alarm goes off is very small. And you might be thinking to yourself, well, wait a minute. So if I shoplift, the alarm's only going to go off less than 1% of the time? Well, actually, no, that's not what we're talking about here. What we're talking about here is random sampling, meaning if I walk into a grocery store, walk into Meijer's, 6 feet away, of course, and just randomly point to somebody and say, okay, you, and just point at someone, and then I force them to walk through those little things, what's the probability that the person I chose is, first of all, a shoplifter, and second of all, the alarm went off? Very small. And the reason that number is so small is because not very many people shoplift, hopefully. Okay, so if I grab somebody, just point randomly and say, you come here and walk through the thing, there's a 91% chance that the person will do two things. First of all, they won't steal it, and second of all, that alarm will not go off. Okay, so we're talking random sampling, not the effectiveness of the actual alarm here. Okay, keep that tree handy because now we have to answer a question. First question, what percent of the bags trigger the alarm? So hopefully we're clear, guys. There's two ways that alarm can be triggered. There's two things. Down here, the alarm can be triggered right here after a shoplifter. So either someone shoplifted and the alarm went off at 0.0095. And then the second way that they can do that, sorry if I can show it to you. The second way that they can do it is they can not shoplift and have the alarm go off at a 0.0792. Add those two up, we have 0.0095 plus 0.0792, and we have a 0.0887, or an 8.9% chance that alarm is going to go off, because there's two ways. But I want you to be aware of that, because in our very first warm-up example, there was 2 in the denominator, and that's going to happen once again. There's 2 ways. So here's what we have now. Here's the way I'm going to ask the question. Of the times the alarm triggers, so what I'm telling you now is that this event has happened. This is given. So we're not talking about random sampling of all the population now. We're only talking about the times that the alarm triggers. All the non-triggerers, you can walk away. We're not talking about you, okay? What percent actually had the shoplifted item? This is what we call given probability. I'm telling you that the alarm triggered. So I want to say, what's the probability that someone is a shoplifter given that the alarm has gone off? Okay? Well, to use the analogy up here, when we talk third class passengers, we only added up the people who were in third class. That was our given. Now what I want to do is I only want to add up the alarm triggerers. Okay? What makes this example harder is that now I'm not talking about whole numbers with people. I'm talking about probabilities which we have already calculated, and that little difference can be tricky. But the times the alarm triggers, there's two ways that you can make the alarm trigger. And we found the two probabilities already, 0.0095 plus 0.0792. The two ways that the alarm can trigger are right here and right here. Now I want to say what percent of those, not all of them, of those actually have the shoplifted item. Well, the shoplifted one is up top. Of the two alarm ones, here's the one that actually set off the alarm with a 0.0095. Now notice, two numbers on bottom, two numbers on bottom. The same number shows up twice. Let's calculate our probability now. We have 0.0095 divided by the addition of 0.0095 plus 0.0792, and we have a 10.7% chance. So when the alarm goes off, there's still only a 10% chance or almost 11% chance that someone has stolen. All right, you try one more example. See how far you can get. Pause it and see if you can write this tree out. All right, the HIV test accurately defines the condition 99% of the time. Whew, good. And also, 99% of the time accurately shows that someone who does not have HIV actually does not have it. So it's 99% effective both ways. When you have it, it says you do. When you don't, it says you don't. It is estimated that not 5%, but 0.5% of the population has HIV. If the test comes back positive, let's underline that. I'm telling you the test back comes positive. What is the likelihood that the person does not have HIV? All right, let's set up the two events that can happen here. Event one is H, so we'll call that someone has HIV. And the second one is, we'll call it P for test positive. Of course, those are not the only letters that you, and make sure it's not that it's positive that you have it, but it's that you test positive. Okay, of course, you could use T or other letters if you want, but that's just what came to mind. So the first thing that has to happen is either you're going to have the disease or you don't. So if I set up my tree over here, I'm going to have H. The probability that you have it is very, very small. H would be not 5, but we're going to slide it 2 places over, so 0.005% chance. Not H would be a bit bigger. It's trickier than you think. I think there's a couple 9s in there. 1 minus 0.005. Oh, no, 1 minus 0.005. I said wrong. So 0.995. That you do not have it. After you have it or don't, you can either test positive, or here's what I would not introduce another letter like an N for negative. What I would call it is not positive. Okay? Same thing down here. Either you test positive or don't need that squiggle. Not positive. So let's read again. The standard HIV finds the condition 99% of the time. Means if you have it, you will test positive, and that should be a 0.99. Here, then this would obviously then, hopefully obvious, be 0.01. Now you got to be careful here, because it accurately shows 99% of the time, it accurately shows that someone does not have HIV. Accurate is a tough word, because if you don't have HIV, accurate means says you don't test positive. So the 0.99 is actually going to go down here and the 0.01 up there. Because if you don't have it, you want it to say that you don't have it. All right, then calculate your intersections. I'm just going to write them behind instead of writing out all the whole, the probability H intersect P and all that. I'm just going to quick write them down. 0.005 times 0.99. So we have 0.00495. 0.005 times 0.01. E negative 5 means 0.00005. 0.995 times 0.01 equals 0.00995, and the last one, 0.995 times 0.99, means we have 0.98505. Okay, once again, I want to reiterate quickly, just because this does not say that, you mean if I have the disease, here's the probability that it actually finds it. That's a garbage test. It's no good. No. This is random sampling. I'm going to walk out in the middle of the street and say, I think you have HIV. Come take a test. And the probability that I actually found someone who, yes, has HIV and also, yes, tested positive would be very, very, very small. And the reason is because almost no one has the disease. All right, if the test comes back positive, that's my given. Given means I'm only talking about positive testers, okay? Those are the only two groups that I'm talking about. It narrows it down. What is the likelihood that the person does not have HIV? So if I want to write it as a formula, I would say, what's the probability that someone does not have HIV given that they test positive? Okay, well, the only groups that I'm talking about are these two groups. Those make up my denominator, 495 plus 0.00995. Now, my numerator is only going to be, let's see, if the test comes back positive, so those are my two positive groups, what is the likelihood that someone does not have HIV? I'm going to pick the not have HIV person to be on top, 0.00995. Once again, note, two numbers make up the denominator. The same number shows up twice. Punch it out and you'll have your answer. So 0.00995 divided by 0.00495 plus 0.00995 together in parentheses. Make sure you get those in parentheses. And we got it as a 66.8% chance. So 0.66778, or we'll call it 66.8% chance. So what it's saying here is this is a very sensitive test. Even when you test positive, there's still a pretty strong strong idea that you don't have it. All right, tough stuff. Do your best. Now, here's how it's going to go. I'm going to give you an assignment. I expect it to be tricky. Do your best on it for a time. Of course, I'll be posting videos to help you out. Friday will be a day off unless you are going to re-quiz. So if you don't need to re-quiz, enjoy a longer weekend with nothing to do. If you are going to re-quiz, the re-quiz will be the only thing that we do Friday. Have a good day.